Hello friends, welcome back to my YouTube channel. This would be fourth part of my discussion on leaching, and in this I will continue my discussion on stage-wise leaching. As far as stage-wise leaching is concerned, this would be the second part on stage-wise leaching. In part number 3, leaching part number 3, I had discussed solid liquid equilibrium, which is important in stage-wise leaching. And in this video lecture, I will be discussing single stage leaching. So in this discussion, you will understand how to write material balances for single stage operation and then how to follow those material balances on the equilibrium diagrams. So let us start the discussion. To begin with, let us know something about stage-wise contact. And in our discussion, to understand that, we are going to consider a simple ternary system. Feed is a mixture of two solids, solid B and solid C. Solid C is the solute that is to be separated by leaching, whereas the other solid that is B is the insoluble solid and it is called the carrier solid. So feed is containing two solids, B and C. Out of this, C is to be recovered by using leaching and therefore it will be soluble in the solvent, whereas the other solid, that is solid B, it is considered to be insoluble and it will not be soluble in the solvent. We call solid B as the carrier solid. Then the solvent used, we are going to denote that by A. The feed mixture, which is mixture of B and C, and solvent A, they are contacted in a stage-wise manner. When these two phases, the feed solid mixture and solvent, they are contacted in stages, you have what is called stage-wise contact. So the feed mixture B plus C and solvent A, they are contacted in a stage-wise manner. Then in order to simplify the analysis, you may assume the following things. You may assume that solid B is not at all soluble in solvent A. That means out of B and C, only C is soluble in solvent A. Solid B is not at all soluble in the solvent A. Of course, this is an assumption. In reality, in some cases, solid B may be slightly soluble in the solvent A. But for simplification, you can assume that solid B is not soluble in solvent A. Then there is no preferential adsorption of either solute C or solvent A on the surface of solid B. So the second assumption is that there is no preferential adsorption of either solute C or solvent A on the surface of solid B. I have discussed the concept in my previous video, but yet I'll tell you once again. So when you have the solid mixture B plus C and when this is contacted with solvent A, then what happens? The solute C, it gets dissolved in the solvent and ultimately you get solution of A and C. Now when the solution of A and C is in contact with the solid phase, there is a possibility that A will get preferentially adsorbed on the solid or C may get preferentially adsorbed on the surface of the solid. But for simplicity, we can assume that there is no preferential adsorption of either solute C or solvent A on the surface of solid B. Then, in order to ensure that an equilibrium is reached between the solid and liquid phases that leave any stage, the third assumption is important. What is the assumption? The quantity of solvent A that is used in the operation, it is enough to dissolve all solute C that is present in the original mixture. So when quantity of solvent is enough, then an equilibrium will be reached between the leaving solid and liquid phases. So the solid and liquid phases that leave any stage in the operation. So the third assumption is the quantity of solvent A is enough to dissolve all solute C N. Now each stage it should have the following provisions. There should be provision for mixing the solid mixture, that is B plus C, with the solvent A, and there should be a provision for settling, filtration or drainage of the resulting slurry of insoluble solid, that is B, immersed in the solution of solute C in solvent A. So when you mix the feed mixture B plus C with solvent A, what is going to happen? It will result in a slurry. The slurry is of insoluble solid B that is immersed in the solution of solute C and solvent A. So once you have this slurry, you need to settle the solids in order to remove the clear solution, or you may need filtration of the slurry in order to separate the solid phase from the liquid phase, or you may have to drain the liquid in order to get the clear solution. So there should be a provision either for settling or filtration or drainage. This is necessary to separate the clear solution of A plus C from the leached solids. So there should be provision for mixing, and there should be provision for settling or filtration or drainage. So if you have to represent it schematically, then you can do it in this way. So the feed solid mixture, which is B plus C, it is admitted into the stage. Then solvent A, it is also admitted into the stage. First, these two will be mixed in the mixer. The resulting slurry will then be transferred to a settling tank where solids will settle, and you will be able to physically separate the clear solution from this. Then the clear solution is removed as overflow, or you can also call it as clear solution. It is actually the solution of A and C, solution of C in A. Then the leach solid, after removing the clear solution, whatever leftover solids are there, they are removed as underflow or leach solids. And leach solids, it will contain insoluble solid B in it, plus it will contain some clear solution associated with the leach solids. And this is due to the fact that no perfect separation is possible. It is not possible to separate all solution from the leach solids. Some quantity of A plus C solution is going to remain with the leached solids. So this is a single stage which has provision for mixing and provision for either settling, filtration or drainage of the slurry that is formed in the mixer. And you get overflow, which is the other name for that is clear solution, which is solution of C in A, and the other stream is underflow, which is leach solids from which most of the solute has been removed. Underflow, along with leach solids, there will be some quantity of the clear solution, that is solution of C in A. Now let us talk about single stage leaching. The feed mixture, that is B plus C and solvent A, they are contacted in a single stage. And this operation could be carried out in a batch-wise manner, or you can carry out in a continuous manner. So let us represent that operation schematically. Let this circle represent the stage. This is stage 1. since this is a single stage operation, so this is the only stage that will be there in the operation. Then feed will be admitted into the stage, and I will shortly tell you what are the notations I have used. Then feed is admitted to the stage, solvent is admitted to the stage. I will tell you what are the notations. Then there will be mixing, there will be settling or filtration or drainage of the clear solution, and then underflow or leach solids will come out. I will tell you the notations. Then the overflow will come out of the stage, and we are assuming that the phases, liquid and solid phases, underflow and overflow that comes out of stage number 1, they are in equilibrium with each other. That is, this stage is considered to be an ideal stage. If it was not an ideal stage, if it was a real stage, then overflow and underflow, they may go close to equilibrium. They will not be in exact equilibrium with each other. But if the stage is ideal, if the stage is theoretical, if the stage is an equilibrium stage, then overflow and underflow, they will be in exact equilibrium with each other. Now let us talk about the notations. In this case, F represents mass or mass flow rate of A plus C in the feed mixture. So mass if it is batch operation, mass flow rate if it is a continuous operation, and this time it is mass or mass flow rate of A plus C that is present in the feed mixture. So this is a different way of defining F. The way F is defined in case of leaching is different. F considers mass or mass flow rate of just A and C that is present in the feed. Then YF, this is mass of C upon mass of A plus mass of C in the feed, which is weight fraction of C on a B free basis that is present in feed. Then NF, capital NF is mass of B divided by mass of A plus mass of C in the feed. That is, this is weight fraction of B on a B free basis and the feed. Then the other notation is S naught. S naught is mass or mass flow rate of A plus C in the solvent. Again, we are just considering A and C. So S naught is mass if it is a batch operation, or mass flow rate if it is a continuous operation of A plus C in the solvent. Then X naught is mass of A, mass of C divided by mass of A plus mass of C in the solvent. That is weight fraction of C on a B free basis in the solvent. Then the other notation is O1. O1 stands for mass or mass flow rate of A plus C in the overflow that is coming out of stage number 1. So O1 is mass or mass flow rate of A plus C in the overflow. X1 is mass of C divided by mass of A plus mass of C in the overflow. That is, it is weight fraction of C on a B free basis in the overflow. Then U1 is mass or mass flow rate of A plus C in the underflow. Y1 is mass of C divided by mass of A plus mass of C in the underflow. That is weight fraction of C on a B free basis in the underflow. N1 is mass of B divided by mass of A plus mass of C in the underflow, which is weight fraction of B on a B free basis in the underflow. So these are the notations. Now let us see what happens in the stage. So when the feed mixture is mixed with the solvent in this stage, what happens? Initially a mixture is formed in the stage. So when feed is mixed with the solvent, when feed enters the stage along with the solvent, initially a mixture is formed in the stage. For this mixture, the notations used are M1, it represents mass or mass flow rate of A plus C in the mixture. So every time we are defining mass or mass flow rate in terms of A plus C. Mass or mass flow rate of A plus C. So M1 is mass or mass flow rate of A plus C in the mixture. Y M1 is mass of C divided by mass of A plus mass of C in the mixture, that is weight fraction of C on a B free basis in the mixture. NM1 is mass of B divided by mass of A plus mass of C in the mixture, that is weight fraction of B on a B free basis in the mixture. Okay, now let us look at the material balance for solids. Material balance for solids B. So it will be written as mass of B in the system, that is equal to mass of B in the feed, that is equal to mass of B in the mixture, that is equal to mass of B in the underflow. That is B that is present in the system. It is in the feed, then it goes to the mixture, and then it goes to the underflow. No B goes to the overflow. So that's why the material balance is written as mass of B in the system is equal to mass of B in the feed, that is equal to mass of B in the mixture, that is equal to mass of B in the underflow. Now let us write it mathematically. So it will be written as mass of B is equal to NF into F, that is equal to NM1 into M1, that is equal to N1 into U1, and I am calling it as equation number 1. Now let us understand how we get this term, NF into F. Now what is NF? NF is mass of B divided by mass of A plus mass of C. I am writing it in short. Mass of B divided by mass of A plus mass of C in the feed. And F is mass of A plus C in the feed. Mass of A plus C in the feed. So B upon mass of A plus C in the feed into mass of A plus C in the feed. So A plus C gets cancelled and you are left with mass of B. So that's why you have this term NF into F. Now let us look at the other term. I'll erase it. The other term is NM1 into M1. NM1 is B in the mass of B in the mixture divided by mass of B in the mixture divided by A plus C in the mixture. Mass of A plus mass of C in the mixture. M1 is mass of A plus mass of C in the mixture. So in the denominator you have mass of A plus mass of C in the mixture. Over here you have mass of A plus mass of C in the mixture. So this two will get cancelled and you are left with mass of B. Mass of B. That's why the term NM1 into M1 is nothing but mass of B in the mixture. Now let us look at this term. I'll erase it. So this is N1 is mass of B divided by mass of A plus mass of C in the underflow, and U1 is mass of A plus C in the underflow. So A plus C in the underflow, A plus C in the underflow, it gets cancelled and you are left with mass of B in the underflow. So that's why you get equation number 1. Equation number 1 tells you or gives you the balance for solids B. So mass of B is equal to NF into F, that is equal to NM1 into M1, that is equal to N1 into U1, and I am calling it as equation number 1. Then let us write material balance for solute C. So it will be written as, I will first write the equation and then tell you how we get that equation. So F into YF plus S naught into X naught, that is equal to M1 into YM1, that is equal to O1 into X1 plus U1 into Y1, and I am calling it as equation number 2. Now let us understand how you get those terms. Now F, what is F? This is A plus C in the feed. Mass of A plus mass of C in the feed. And what is YF? This is mass of C divided by mass of A plus mass of C in the feed. Mass of A plus mass of C in the feed. So mass of A plus mass of C in the feed, it gets cancelled out and you are left with mass of C. Now let us look at the next term, the second term that is present in the equation. So it is S naught, this is mass of A plus C in the solvent and x naught is mass of C upon mass of A plus mass of C in the solvent. A plus C gets cancelled and you are left with mass of C. So in the same way, you can get explanation for the other terms as well. So M1 is mass of A plus C in the mixture. Ym1 is mass of C upon mass of A plus mass of C in the mixture. And mass of A plus C in the mixture, that gets cancelled out. So you have A plus C in the mixture, and this is C upon A plus C. So every term is product of this two quantities. A plus C in that particular stream into C upon A plus C in that particular stream. So everywhere A plus C is going to get cancelled and you are left with C. So it will be mass of C in the feed plus mass of C in the solvent. Mass of C in the feed plus mass of C in the solvent is equal to mass of C in the mixture, that is equal to mass of C in the overflow plus mass of C in the underflow. So this is how you get equation number 2 when you write material balance for solute C. Now let us write material balance for the solution A plus C. So it will be written as F plus S naught, A plus C in the feed, S naught is A plus C in the solvent, M1 is A plus C in the mixture, O1 is A plus C in the overflow, U1 is A plus C in the underflow. So that's why material balance for solution A plus C, it will be written as F plus S naught is equal to M1, that is equal to O1 plus U1, and let us call this as equation number 3. So we have got equation 1, which is mass of B is equal to NF into F, that is equal to NM1 into M1, that is equal to N1 into U1, and this is equation number 1, which we got earlier. Then equation 2 was F into YF plus S naught into X naught, that is equal to M1 into Ym1, that is equal to O1 into X1 plus U1 into Y1. This was equation number 2. And we got equation 3, which is F plus S naught, that is equal to M1 plus O naught plus U1, and this is equation number 3. Now from equation number 1, I can write mass of B is equal to NM1 into M1. So from equation 1, I can write this equation. Mass of B is equal to NM1 into M1. Therefore, NM1 is mass of B divided by M1. So when this M1 comes on this side, we will get equation for NM1. So NM1 will be equal to mass of B upon mass of B divided by M1. And if you use equation number 3, where M1 is expressed in terms of known quantities, which are the known quantities? M1, F and S naught will be initially known to you for the single stage operation. So in place of M1, you can write F plus S1. So with equation number 3, M1 is F plus S naught, and if you use it in this equation, NM1 will be equal to mass of B divided by F plus S0. So this equation is useful for calculating NM1, which we need in our analysis. Then again from equation number 2, you can write this equation F into YF plus S naught into X0, that is equal to M1 into Ym1. That is Ym1 will be equal to F into YF plus S naught into X naught divided by M1. And M1 you can write from equation number 3, it is F plus S naught. So therefore Ym1 will be equal to F into YF plus S naught into X naught divided by F plus X naught. So we have got an equation for Ym1 where every quantity that is present on the right hand side of the equation is known. So you can use those known quantities and get the value of Ym1. Similarly, in the equation for NM1, all quantities on the right hand side are known to you. So you just have to use those quantities to get the value of NM1. So at the end of this particular discussion, we now have equation for NM1 an equation for yn1. That is, we are now in a position to calculate nm1 and ym1 because this too will be useful in our further analysis. Now, we will follow all those material balance equations on the equilibrium diagram. So, what is this equilibrium diagram? We are going to plot nx and ny on the y-axis, x and y we are going to plot on the x-axis, and the plots are obtained in this way. X is plotted against nx and y is plotted against ny. X is plotted against nx, y is plotted against ny. So, you are plotting nx and ny on the y-axis, x and y on the x-axis, nx is plotted against x, ny is plotted against y. So, you get x versus nx curve, you get y versus nx curve. So, if this curve will coincide with the x-axis if there are no solids in the overflow. I have explained this concept in my earlier video. You please watch it. I am giving link to the playlist of all my videos on Leaching in the description section. You please watch those videos. Our first task is to locate F. So, for locating F, we are going to use YF and NF. Point F will be located at YF, NF. So, you just have to locate YF on the x-axis, draw a vertical line through it. Then you have to locate NF on the y-axis and then draw a horizontal line. So, in the process, you are going to get this point, this intersection point. So, this point has coordinates of YF and F, and we are going to call this point as point F. Then next, you have to locate S0. S0 will be located at x is equal to x0 on the x versus nx curve. So, x versus nx curve will come into picture when there are solids in the overflow. If there are no solids in the overflow, this curve will coincide with the x-axis. So, in that case, point S0 will be located at x is equal to x0 on the x-axis. So, I am showing when the curve is above the x-axis. Most of the time, the curve will coincide with the x-axis because there will be no solids in the overflow. So, point S0 has to be located at x is equal to x0. So, I will mark x0, go to the curve, and then I will locate point S0 over here. And next task is we are going to connect F and S0. So, F and S0, these 2 points will be connected with a straight line. So, in this way, you get the straight line. Then, the next task is to locate M1, point M1. And it will be located at a point whose coordinates are ym1 and m1. And plus it will be located on the line F, S0. So, for that, we need to find out ym1 and nm1. Nm1 is given by this equation, mass of B divided by F plus S0. And ym1 is given by this equation, F into Yf plus S0 into X0 divided by F plus S0. Then you can use either one of this because the other known thing is point m1 will be located on the line F S0. So, knowing one point, one value, either nm1 or ym1 is sufficient for us. So, let us either nm1 or ym1 can be used, as I said. So, let us use nm1. So, nm1 will be located on the y-axis. So, nm1. After locating it, go to the line fs0 where the intersection occurs. That will be nothing but point m1. And if you get the x coordinate of this point, that x coordinate will be nothing but ym1. So, that means you can either use nm1 or ym1 for locating the point m. Now, we have to draw a tie line through m1. If C is adsorbed, that is, you have different values of X and Y. X and Y, they are not equal. That means solute C is adsorbed. So in that case, you have to draw a tie line, and that tie line is not vertical. So that tie line, it has to be drawn by trial and error. A tie line that passes through M1, you need to draw it by trial and error. If solute C is adsorbed, or if you have different values for X and Y, they are not equal, then tie line is not vertical. You have to draw it by trial and error. So it will be passing through point M1, and you have to take reference of the given tie lines. So in my next video, I have solved one numerical based on single stage leaching. There I have told you how to draw the tie line by trial and error. The approach is similar to the one which was used in the case of liquid extraction. So we need to draw a tie line that passes through point M1. If solute C is adsorbed, tie line will not be vertical, and in that case you will have to draw it by trial and error. Endpoints of this tie line are O1 and U1. You have to name. O1 will be the endpoint on the lower curve, that is NX versus X curve, X versus NX curve, and U1 will be the endpoint on Y versus NX curve. You please note on this diagram, O1 is representing a point and U1 is representing a point. Whereas in the material balance equations, U1 and O1, they are representing quantities. You please remember it. The x coordinate of O1 is x1. So you just have to read the x coordinate of O1, that will be x1. You just have to read the x coordinate, it will be x1, and the x coordinate of point U1 is y1. So the x coordinate of tangent U1, let me just show you. The x coordinate of point U1 will be y1. So the point is, in this case, x1 and y1, they will be known to you. X1 and y1, they will be known. Now let us learn how to draw tie lines through M1, the desired tie line, if solute C is not adsorbed. So if solute C is not adsorbed, then X will be equal to Y, and in that case the tie line will be vertical. So you just have to draw a vertical tie line, and the endpoints are again O1 and U1, and O1 on the lower curve, E1 on the upper curve. The X coordinate is x1, y coordinate is y1, as I said it earlier, and in this case x1 is equal to yb. So in both the cases, if C is adsorbed, we get x1 and y1, and if C is not adsorbed, you get x1 and y1. The point is, at the end of this calculations, now we know values of x1 and y1, and we are going to use these values in our further calculations. Let us understand. Okay, now let us understand how to calculate the quantities of overflow and underflow. Overflow is O1 and underflow is U1. So for that, we are going to use equation 2 and 3. Equation 2 is F into YF plus S0 into X0, that is equal to M1 into YM1, that is equal to O1 into X1 plus U1 into Y1. This is equation 2. And equation 3 is F plus S0, that is equal to M1 plus O1 plus U1, that is equation 3. So now we can write these equations from 2 and 3. F plus Y, F into YF, that plus S0 into X0, that is equal to O1 into X1 plus U1 into Y1. And from equation 3, you can write F plus S0 is equal to O1 plus U1. So you have these two equations. Let us say this is equation number 4 and this is equation number 5. So in equation number 4 and 5, F, S0, X1 and Y1, they are known to you. So the only unknown quantities that are left, one is O1 and U1. So you can solve equations 4 and 5 simultaneously and get the quantities of overflow and the underflow. So in this way, you can calculate the quantities of overflow and underflow. So with this, I end my discussion for single stage leaching. Here, I have told you the theoretical aspects of single stage leaching, how to write material balances for solids, then material balance for solute, material balance for solution A plus C, then how to follow this material balances on the equilibrium diagram, then how to draw the required tie line if there is no adsorption of solute C, and if there is adsorption of solute C, there you'll be getting x1 and y1. Then how to use x1 and y1 to get the quantities of overflow and underflow I have just now explained. So with this, I end my discussion for today's video. In my next video, I will be solving one numerical that is based on single stage leaching. So whatever you have learned in this video, we will apply that in the next video to solve a numerical based on single stage leaching. So for now, I will end my discussion for this video. So as I said, the two equations can be solved simultaneously to get O1 and Y1. So with this, I'll end my discussion for this video. Thanks for watching this video. Do subscribe to my channel. Tell your friends to subscribe to my channel. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day. Bye bye and take care.